temperature measurement and everything to do with temperature measurement, all the little problems you get with temperature measurement, and how we go about measuring temperature. Now, the first thing we're going to talk about is what temperature isn't. Temperature isn't heat. Heat is energy, and energy is the ability to do work. Energy is, if you look at the energy contained within an atom, it's the kinetic energy of that atom, which is how fast it's moving, and potential energy. Potential energy is just a word for the bits we can't see. The unit of heat, the unit of energy, is the joule. The old unit of energy was the calorie. The American unit of energy is the truly all-American unit, the British thermal unit. Heat will travel from a high temperature to a low temperature. Now, temperature, on the other hand, that's a number, and that number relates to how fast the molecules are moving. You see, these molecules down here, grab me pointer. These molecules, oh, that's a terrible pointer. These molecules down here, they're all skittering around, and they're all moving at different speeds. Oh, that's possibly not what I want to do. So that this one could be moving in that direction, and that one moving in that direction, this one moving in that direction. Every now and then, one of them hits a surface and bounces back. They also hit each other, and when they hit each other, like balls on a pool table, they transfer energy from one to another. Temperature is a measure of how fast the molecules are moving. Oh, sorry, Russell, did you want me to wait? Right, so temperature is this number which tells us how fast the different molecules are moving. Some time ago, a chappie called Kelvin, he came up with the idea that if temperature is actually the speed at which the molecules move, there must be a speed at which they don't move. There must be a temperature which corresponds to them being stationary. And he did a bunch of experiments and some calculations, and he worked out that absolute zero, which is as cold as it can possibly get, and it can't get any colder than this because molecules can't get any more stationary than not moving. So absolute zero was minus 273 Celsius. And he said, right, I'm going to call absolute zero 0 Kelvin after myself. And 0 Kelvin is minus 273 Celsius. 273 Kelvin is 0 Celsius. 373 Kelvin is 100 Celsius. That's pretty well the definition of the centigrade scale, actually. So the official SI unit of temperature is the Kelvin, but no bugger ever uses it, so everybody uses Celsius. And if you want to go from Celsius to Kelvin, you just add or subtract 273 each time. Heat goes from one thing to another. It generally goes from the hot object to the cold object. There's several ways that heat will travel. The first way heat travels is by conduction. Basically, if two objects are touching, so if I've got a hot object and I've got a cold object and they're touching, then heat goes from the hot to the cold. That's the first way that heat travels, conduction. The second way is convection. Convection is, if I have a pot full of some sort of fluid, and I have a hot, oh, that's not what I wanted to do. I have a hot object at the bottom, then heat will travel, the fluid will be heated, and as the fluid is heated, the density of the fluid decreases, and as the density of the fluid decreases, it tends to rise. So it tends to rise. Now, as the liquid or the fluid rises, it leaves a hole. So other fluid flows in to fill that hole. So where that fluid flowed in, that leaves a hole. So other fluid flows down to fill that hole. And you get the hot fluid then flowing across. Now we have a thing called a convection current, where the hot object here is transferring its heat via convection upwards, but that is turning round and cold fluid is coming in. Basically, if we've got something like a kettle, an electric kettle or an urn, just above the element, the fluid will rise. Other fluid flows in to replace it. This is quite important because if we're measuring temperature, if I've got a temperature sensor just there, it will tend to read quite hot temperatures. Whereas if I have a temperature sensor just here, it'll read a lower temperature because this temperature sensor is immediately above the hot object, so it's getting the hot convection current. Whereas this temperature sensor is getting the cold part of the convection current. So convection currents are important, and it makes a big difference where you put your temperature sensor. You could have 2 or 3 degrees difference between the two temperature sensors. Another way that temperature, I should go back to that, another way that temperature transfers is by radiation. Radiation is when energy just travels through, energy travels as particles. Now what you get is, you get a particle of, I really want that to be read. You get a particle of energy that travels along quite happily through the universe. It's traveling in this direction. Particles of energy are called photons. That's a photon. So I've got a particle of energy traveling along quite happily. As it travels, it tends to travel in a wave form, so that we say that energy travels in particles and it also travels in waves. Now, any object that warms up, any object that contains energy, will output photons of energy. Those photons of energy will travel, they don't need anything to carry them, so they'll travel quite happily through vacuum. I'm just going to keep going, and hopefully Julian will catch up with us. Okay, so energy will travel through a vacuum, and that's a good thing because that's the energy from the sun travels happily through the vacuum of space and comes and warms the Earth up. So that's an extremely good thing. There are some particular frequencies of the electromagnetic spectrum that just happen to be really good at warming up water. Now, we, as human beings, are basically bags full of water. So if you can find the right frequency for warming water up, we tend to say that frequency is good for warming us up. Frequencies that are really good for warming water up are in the infrared. Basically, the infrared will warm water up. Now, There are other frequencies of the electromagnetic spectrum which are also good at warming water up. Does anybody know another frequency of electromagnetic that's also good at warming water up? Yep, you've got it. Microwave, which is, lives over here somewhere, I think, in the radio frequencies. So microwave lives over that way. Microwave is also good at warming water up. In fact, you could probably make an oven out of that. That's another area which you would say is, it carries heat, if you like. If you hit us with microwaves, we get warm. We also get sterile, but, you know, that's besides the point. So, moving along. Sometimes we pump heat into an object and it doesn't heat up. Sometimes we pump heat into something and we don't see a temperature change. I think with some of you I did a little experiment. Basically, if I have a pot and inside that pot I've got a big chunk of ice and where's my pen? And I heat this pot up by sticking flames underneath it, I get to, say, 100, no, not 100, what am I saying? I get to 0 degrees C, and I no longer see any temperature rise. So leading up to this point, if I've got a graph, time along there, temperature up there, I've been seeing a steady temperature rise, and then suddenly I get to 0 degrees C, and I don't see any temperature rise. Now, what's occurring? What's happening? Why isn't my ice warming up anymore? It's melting. It turns out that when it's changing, yes, you're right, it's changing to water. It turns out that when you change state from solid to liquid, or when you change state from liquid to gas, when you change state, it's not free. You have to pay for the privilege of changing from a solid into a liquid, and you pay in energy. So you have to pump energy into something to change it from a solid to a liquid. Now that energy doesn't appear as a temperature change. It goes in and it's used up to change the state. So you can pump energy into it and you don't see any temperature change because all the energy is being used to change state instead. What's actually happening on a technical note is it's breaking molecular bonds.